Hello everybody, welcome to the final third lecture series of this academic year. Today we are glad to have Dr. Sierra McGrath from our own university. She is a lecturer at the Aerospace Systems, and she is the IET Young Woman of Engineer in the year of 2021. Dr. Sierra McGrath is the expert in space mission design, and her focus is how to develop a more sustainable space missions. And she is also dedicated to trying to bring that topic to a wider audience, including students from all disciplines. So let us give it for Professor Sierra McGrath for the topic covering the sustainable space race.
Great, thank you very, very much. And I'm really, really delighted to be here, and thank you for inviting me, because I know it's been a while to set this up, so I'm glad that we finally managed to actually make it happen. Yes, so my name is Kira. I am a lecturer in the Aerospace Engineering Department, and my expertise is in astrodynamics and space mission design. So essentially thinking about when we design the space missions of the future, how do we plan them to be able to get the data or the science that we need? Where do we put the satellites? How many satellites do we need? What do those satellites need to look like? But for context, in recent years, what I've been starting to think about is how can we do this in a more sustainable way? And this has really been the focus of what I've been looking at for the last while. So since it's quite a small group, I think we can take it as we go. So feel free to stick your hand up and ask a question if you want as we go, or you can wait till the end. It's entirely up to you. But I'm really happy to have a conversation about this. It's not going to be too technical. It's really about the vision that we have for the future, where we've come from and where we think we're going. So I'd love to hear your opinions and thoughts as we go. So in order to think about where we are today in space, I think it's really helpful to go back to the beginning and think about where we've come from. So if we go all the way back to 1957, it was back then that humanity launched their first satellite into orbit, Sputnik 1. And quite frankly, it didn't really do very much. But fast forward a decade, and by 1967, we now have over 100 active satellites in orbit around the Earth. And they're starting to be able to do really incredible things, like map the surface of the planet in a way that was never possible before, and taking really high resolution images primarily for military purposes. Fast forward another 10 years, and we've got another 100 satellites in orbit. And now we've really progressed our technology. And we can start to send our satellites much further away from the Earth. So it's through this decade that we start sending our satellites out to what we call geostationary or geosynchronous orbit. So those are orbits that are 36,000 kilometers away from the Earth, so really far away. But from that distance, we can start to get images of our entire globe, and we can use these for really useful things like weather forecasting. Another 10 years and another 150 or so satellites now in orbit by the late 80s. And during this decade, we start seeing something really cool come online, which is something that we call synthetic aperture radar. So before this, a lot of the satellites that were taking pictures of the Earth were doing it using normal optical cameras, which work a bit like our eyes. They're taking in light and giving us an image. Synthetic aperture radar is a radar instrument. And so the satellites themselves actually generate their own signal, which they send down to the Earth. It bounces back off the planet, and they receive that signal. And based on the signal that they receive, they can create a picture of what it's looking at on the Earth. And the really cool thing about this is it gives a different view of the Earth to optical imagery, which is useful, but even better, you can see through cloud. So for anyone who spent any time in Manchester, you can imagine why this would be really, really useful. Another decade, and we've now got another about 200 or so satellites in orbit, so we're now up to about 600 satellites. And what's really nice at this stage, What's really nice at this stage is that some of these satellites have been in orbit for a really long time. So this is an image from the same synthetic aperture radar satellite I showed from 1987. So that satellite's been on orbit collecting data for that 10 years. And so what that's allowing us to do is to start to build up this picture of what our planet looks like and how it's changing over time. Another 10 years, and we've got a few more satellites going up than we had previously. So we've now got an extra 300 or so in that decade. So it is ramping up a little bit, but not too much. But this is when we start to see a real change in the quality of the imagery that we can get from these satellites. And again, because we've got so many of them now, we can start to look at how things are changing, not just over decades, but over the course of years, days, and even months. But the next decade is when we start to see a huge jump. So suddenly we've got a doubling of the number of satellites that are in orbit. We've gone from 900 active satellites to nearly 1,800 in 10 years. And it's this era that we often talk about as being the new space age, or the new space era. And it was a really exciting time. It's when I started out on my career. And it's a time when it felt like anything was possible. Space was changing really rapidly. We were able to build satellites much more cheaply and easily and launch them much more cheaply and easily. And everyone was talking about this idea of the democratization of space. That we were moving towards a stage where previously all of these satellite missions required so much money and expertise that they had to be designed and built by wealthy countries, specialized agencies like NASA, or very, very big corporations like people like Boeing and so on. But suddenly, the whole area of space was open to so many more people. So we moved into a stage where universities, schools, small companies, developing nations could all start to develop and launch their own satellites. And that's partly why we saw this great increase in numbers. But one of the other things that happened then, which is really cool, is that we also saw a democratization of space data. So the Copernicus program, which is run by the European Space Agency, was started during this decade. And they launched a series of satellites called the Sentinels. This is an image from Sentinel-2, which is the one that has an optical camera on it. Sentinel-1 has the radar, which I talked about before. But what the Copernicus program did, which was different to what had come before, was they made a commitment that every bit of data that was gathered by these satellites would be made publicly available to anyone in the world with no request required. So you can go online, anyone can, and access all of the data from all of these satellites dating back to when they were first launched. And so suddenly what that meant was that people were able to start businesses, they were able to do research by accessing all of this data and using it for things that nobody had ever thought of before. But now I'm going to jump forward just 5 years. So previously we've been jumping in decades, now we're going to jump forward 5 years. And this is when we see the real explosion in the number of satellites that are going into orbit. So we were on 1,800, so about 2,000. We've now tripled, quadrupled, nearly, up to 7,000 spacecraft in orbit at the end of 2022. And I don't have updated numbers for 2023 because I can't get accurate numbers. But the best guess I can get at the moment for how many active satellites we have in orbit today is about 9,500 to 10,000. So there are a lot, and it was a real explosion in that 5 years of all of these satellites being put into orbit. And a lot of them were from SpaceX, the Starlink satellites, which are aiming to bring internet, essentially, to areas that currently don't have connectivity. But there was lots of other things as well. Things like PlanetScope. So Planet was a company whose goal was to use tiny satellites, CubeSats, that are about the size of shoeboxes, and launch them up into orbit to take really high clarity images of everywhere in the world every single day. And so they have on the order of about 100 or so spacecraft in orbit at any one time, and they're providing that really high frequency of imagery so that we can see how things are changing really, really quickly around the globe. And that's starting to enable some, again, a commercial company starting to enable some really cool new things. So for me, having all of these spacecraft in orbit and having that access to satellite data is a really exciting time to be a part of this industry. Because one of the things that I think people forget about is that when we think about space and satellites, we often think about, going to the moon, going to Mars, looking out into deep space to study, astrophysics and so on. But actually the vast majority of the satellites that are out there are are in orbit around our Earth. They're very, very close to us, less than 1,000 kilometers above our head, so closer than Germany. So very, very close. And their goal is actually to provide services to us here on Earth. So to give some examples just from things that I've worked on personally, we have satellites that are providing imagery of natural disasters as they're happening, so that we can try and get that data to first responders on the ground and help them to save lives as efficiently as possible. We've been able to use satellite data to monitor archaeological sites and even identify buried archaeological cities that we didn't know were there before. And that can help us to protect these sites, which are of real importance in cultural heritage, monitor them and make sure that we flag any damage that might be happening to these sites before we lose them forever. And we can monitor our natural environment, so whether that's looking at farming, climate change, or in this case, looking at how sea estuaries are changing over time. And we've actually been able to use this data to help lifeboat operators navigate more safely when they're called out in an emergency situation, because they have a much better idea of where is safe for them to travel in their lifeboat and where isn't. So all of that is incredible that we can do all of this today with satellite data, and it really does underpin so much of our lives that we just take for granted. And that's just looking at imagery, but without even thinking about things like GPS and navigation services, communications, TV, and internet. But all of this does also come with an impact. And traditionally, the satellite industry or the space industry has kind of not had to worry too much about its environmental impact, because it was felt that we weren't doing too many missions, they were all so specialized, and they were all so important. But now that we're moving into an era where the space industry is becoming more commercial, it's becoming more open, and it's becoming more prolific, suddenly these impacts are something that we have to take quite seriously. So if we go all the way back to the start of when you look at designing and building a satellite, there's actually quite a lot that goes on here that has an impact here on Earth. So right from the design process, where you've got people working in offices, commuting, traveling around the world to have meetings about how we build these satellites, all of that has emissions associated with it. And when it comes to actually building and testing the satellites, we have a tendency to use some really specialized materials in our satellites, particularly for the special instruments that we might need, the solar panels, things like that. And those can need to be mined. They might be quite precious and rare, and so there's an impact in how we choose to build our satellites, making use of those resources. And of course, we'll move on to launch. I think this is one of the most obvious places where we can think of there being a serious environmental impact. Obviously, you'll have heard about people like SpaceX who are looking at reusable launch vehicles, and that is incredible, and it will make a big, big difference. But regardless of whether the rocket itself is reusable, it's going to need to burn massive amounts of fuel to lift all of those satellites into orbit. And so there's emissions coming from that launch itself. But what's really concerning is that because the rocket is traveling up through the atmosphere, those emissions are being ejected at higher altitudes than we're used to seeing. And there's a concern that they might actually be more damaging to the upper atmosphere than if they were just emitted at the surface of the Earth. And we really don't fully understand that impact yet. And of course then after launch, for reusable launch vehicles, of course we're trying to capture and land and reuse as much of the rocket as possible. But for non-reusable launch vehicles, we're still leaving bits of our rocket either in orbit or else dropping it into the ocean, or in some really not great circumstances onto land, where they can have really bad consequences for the local environment. Then we've got the satellite in orbit, but up there, there's still sort of impact or environmental impact concerns that we need to think about. Not about our Earth environment, but about our orbital environment. This is an image from back in 2022 that's representing all of the satellites, the active satellites that were in orbit at that time. And so you've probably heard about the challenges around space debris and the risks that we have of satellites essentially crashing into each other, crashing into dead satellites, crashing into bits of rocket and so on, and destroying the satellite mission. And the reason that that's such a risk is that all of these satellites are traveling at about 7 kilometers per second, which is really fast. So at that speed, even a fleck of paint can act like a missile. The other thing that people often say, though, is, well, space is really big. Is there really a risk of these things crashing into each other? And the answer is yes. We have seen it happen in the past. Oops, I've gone too far. We have seen it happen in the past. We have seen it happen in the past, but it's not very common. Well, part of the reason it's not very common is that we tend to move our satellites to try and reduce the risk of collisions occurring. And again, when I started out in my career 10 years ago, the idea of people moving satellites to avoid a collision was the kind of thing that might happen once or twice a month. And now it's the kind of thing that's happening multiple times every single day. So it's become a much bigger issue. But part of the reason it has become such an issue is that not all regions of space are as popular as the others. There are some orbits that we really, really like because of various different things about them, and those are the ones that are starting to get really crowded. So if you can see here, there's kind of these little stripes of satellites running down here and down here. Those are satellites that are in what we call quasi-polar orbits. So they're satellites that are going to nearly pass over the north and the south poles. And so those satellites, are going to go back again. Those satellites are in orbits that are really, really popular because they'll be able to see every point on the globe as they travel around. And so it's really useful for lots of different purposes. Something else you might be able to see is there's kind of what looks like a little band of satellites running here around about 50 to 60 degrees latitude. And that's because the Starlink satellites, a lot of them are in an orbit that's inclined at 50 degrees latitude. So essentially, they'll only cover the region between about plus 55 degrees latitude and minus 55 degrees latitude. And the reason for that is because that's where most of the population lives, and that's where most of the commercial benefit is for companies like SpaceX, who are trying to deploy internet from space using the Starlink satellites. And I think this thick train that you can see up there is a new Starlink launch, because they launched them all together and then spread them out into orbit afterwards. The green ones that we saw before, those were just active satellites. This, with the yellow and red, is now including inactive satellites. So satellites that have stopped working for whatever reason, maybe they've got to the end of their lifetime. You can imagine when we were sending them up in the 60s and 70s, we didn't really have a great backup plan for what to do when they finished their mission. Or they're rocket bodies, so bits of rocket that have been left behind from the launches that put them up there in the first place. And if we think about all of the little shards of space debris, then we get into the hundreds of thousands of pieces up there. And those are going to be clustered around those popular orbits as well, not evenly spread around. So that is why this is actually, even though space is big, it actually is still something that we really need to consider. So thinking about where we put our satellites, do we still want to keep putting them into those really popular orbits, or is there a better way? Another impact that you may be aware of for all these satellites is not just when you're in orbit and trying to avoid crashing into each other, but also the impact that they have on ground-based astronomy. So all of these satellites, as they're passing overhead, will reflect light from the sun. And so when they pass across the field of view, you've got long exposure instruments on the ground who are looking into deep space to study planets, exoplanets, who knows what out in deep space, incredible astrophysical phenomenon. And because they need a long exposure to capture those things, they're ending up with huge numbers of streaks across them as these satellites pass across the sky. If you go out stargazing, you don't have to stand around for long before you'll see a satellite pass overhead these days, which is really cool, but also a big problem for ground-based astronomy. And one of the more recent developments in this area, and actually Manchester are really leading at looking into this, is that it's not just about the optical regime that there's a challenge, it's also in the radio spectrum as well. So Jodrell Bank, as you'll know, has a really big radio telescope. We're also involved in the Square Kilometre Array, which is a huge radio telescope essentially that's being deployed across the globe. Normally, satellites are only allowed to communicate in certain frequencies. And so the frequencies that satellites communicate in is really highly regulated. And that's one of the few areas actually of satellite design that's really regulated. And so we'll make sure that they're not going to be transmitting in a frequency that will disrupt these radio telescopes while they're passing through the telescope field of view. But it turns out that as these satellites are just toddling around doing their day-to-day thing, they are actually producing some electromagnetic signals. And that's just because of the different electronics on board that are operating, and they're giving out this sort of low-frequency background radiation. And that was never a problem before, because there wasn't that many satellites and they were all different. So when they passed over, you get a little blip if it happened to be in the frequency you were observing, and then it will be gone. But because things like Starlink are being built en masse and they're all kind of the same, they're all transmitting these electromagnetic frequencies in the same band, and so therefore we're getting a high density of these emissions being picked up on radio telescopes. So that's something that we hadn't really predicted being a problem, but is suddenly starting to become an issue as well. Now, all these satellites aren't up there just for fun and to look pretty. They are doing amazing things like we talked about right at the start. But actually, this is something else where we're starting to be a little bit concerned about things. You'll all be aware that the amount of data that we're all generating and using on the ground has problems in terms of the storage and the amount of energy that's being required for server farms to store and manage all of this big data that we're all creating. And of course, satellites are no different. So if you think about all of the satellites that we've built that are collecting all of this incredible imagery, it's amazing that it's all been stored from the date the satellite was launched and that you can access it anywhere in the world, anytime. But that means that all of that data has to be held and stored and processed somewhere. And so there is this question of how do we try and balance that? You know, some of those images might be of areas of the Earth like the ocean that aren't particularly useful for studying in that way with optical images. Some of them might be cloudy, just full of clouds. So that's probably not much use to anyone either. So there's a balance here between choosing what we choose to keep for the future, because it might be useful in the future, versus what we need to get rid of so that we're not just overloading our servers and our capabilities with what we're trying to store. Finally then, when our satellite gets to the end of life, what do we do with it? So I mentioned that back when we were launching these things in the 60s and 70s, we didn't really have a good plan for what to do at the end of our missions. We have now gotten a bit better at this, and we do try and plan for it, but there is still a limit to what we can really do. So essentially, at the end of a satellite's life, we basically have two main options. For the satellites that are far away from the Earth, so in those geosynchronous, geostationary orbits that I talked about, 36,000 kilometers away, what we tend to do is we use the last remnants of fuel on board at the end of the mission to move them into what we call a graveyard orbit. And that's an orbit that's just slightly further away from the Earth than where they were before, but it's not a really useful orbit for anything. Whereas the orbit they were in before is a really popular orbit, it's really useful, so we want to keep that clear of clutter as much as possible. So we move them out into this graveyard orbit, and we know from the simulations that we've done that they will be able to stay there for on the order of a couple of 100 years without crashing into each other, without crashing into anything else. So we just leave them there essentially in that graveyard. The second option that we have, which is normally what we do for satellites close to the Earth, is that we use the last remnants of fuel on board to move them to an altitude that's closer to the Earth, where there are remnants of atmosphere. And within that sort of very, very rarefied atmosphere, they will still experience some form of drag. And that will slow them down until they start to spiral down into the atmosphere, where they'll eventually heat up and burn up in the atmosphere, either completely or enough that just small scraps will land normally in the ocean. So we can do that using the last bits of fuel on board, or we can put our satellites into lower orbits when they start out, and then at the end of their mission they can just naturally burn up as well. But of course all of that relies on us having enough fuel left at the end of our mission to be able to do that, and to not have our satellite break unexpectedly. We lost EnviSat. It's one of the biggest satellites we've ever launched. It's about the size of a double-decker bus. It had reached the end of its mission life, but it was still functioning, so we decided it's doing great science, let's carry on, and then it unexpectedly broke, and we never had a chance to deorbit. So we now have something the size of a double-decker bus uncontrollably flying through space in one of the most popular orbits. So with the best will in the world, we can still have things go wrong, which mean that we end up with a less than ideal end of life for some of our missions. And of course you'll have noticed that all the things I've talked about up till now are only focused on Earth. But actually, we of course send satellites beyond Earth. We send them out to the Moon and to Mars and to Jupiter and Saturn and deep space. And we need to think as well about how we want to manage those environments when we start traveling further away from the Earth. So if we think about the Apollo missions have left all sorts of things all over the Moon. They've left science experiments, they've left personal mementos, there's tributes to fallen astronauts, there's just general junk that we didn't want to bring back to Earth. Again, that was something they were sort of once-off missions, it wasn't a big thing, but we're now looking at going back to the Moon and going on to Mars. And in fact, on the last Artemis launch, which headed out, it took about 10 small satellites with it, which it placed into orbit around the Moon. And of those, only 3 of them actually functioned the way that they were supposed to. So essentially, 7 broken satellites were dumped into orbit around the Moon as well. And as we start doing more of these launches, as we start sending people back more frequently, suddenly I think we need to start asking ourselves, what is the legacy that we want to leave on these other bodies for future generations? Obviously, we want to be able to explore them. There's amazing science to do. We're talking about building habitations, and all of that is going to have an impact on the environment. But we need to think about what it is that's important to preserve as well. So I have to say, I feel like when I get to the end of this bit, I'm like, this is all really doom and gloom. But what I will say is, in Europe, and particularly in the UK, we are really, really aware of this, and we are really leading in trying to find ways to tackle this and continue to use space for all of the amazing things that we need it for, but do it in a way that's responsible. So the European Space Agency has an amazing clean space program that's looking at a lot of this. Within the UK, we have some of the best companies in the world looking at how we can remove debris from on orbit, so dead satellites, dead rocket bodies, and also creating new ways of allowing satellites to be removed from orbit at the end of their life, naturally or as part of their mission life cycle. And the UK government has committed to being a responsible leader in space. And we've got a memorandum of principles that lots of companies and academic institutions have signed, including the University of Manchester, committing to all of the different, to mitigating all of the different impacts that we've just discussed. So it's actually a really exciting time to be in the UK while this is going on. And so at the University of Manchester, specifically within our research group, the way that we're trying to tackle this is that we're trying to take a big picture view. What we've seen is that there's lots of companies and organisations, like I've mentioned, who are looking at small areas of this problem. So looking at how can we make rocket propellants greener so that they have less of an impact. Looking at reusable rockets so that we're not leaving bits of rockets behind or having them land in the ocean. There's lots of people looking at how we reduce the amount of debris on orbit and how we remove that as well. But what we're trying to do is take a big picture view and think about when we start designing the mission right at the very beginning. What are the decisions that we can make then that can impact every single stage of the satellite's life cycle and make it essentially as sustainable as possible right from the outset. So rather than trying to tackle one of these problems, which might inadvertently make another issue worse, we want to try and look at it holistically and understand how all these pieces fit together. So can we choose our orbits in such a way that we're reducing the risk of colliding with other satellites, perhaps by picking a less busy orbit to put our satellite in? Can we also pick our orbit so that we reduce the impact on ground-based astronomy, for example? If we come lower, closer to the Earth, we'll move across the field of view faster. That might be better. If we go further away, we'll be less bright. So there's different things that we can do right at that first design step to think about how we can reduce our impacts across the entire mission life cycle. And of course, it's going to be a balancing act. When you change one thing, there's going to be a knock-on effect throughout the whole process. But we want to try and find a way to understand that and find the best solution that still gives us all of that amazing space data, but in the most responsible way possible. So, when I look at all of those satellites that are in orbit now, or back in 2022, I do see a real challenge. But I also see all of the incredible data and services that these satellites give us here on Earth that underpin so much of our life today that we take for granted. And if we lose those, we would just lose so much. We would lose our entire way of living. So, can we win the sustainable space race? I believe that we can, but I think that we need to stop dealing with the immediate problems that we're facing. We need to stop being reactive to the issues that are appearing, and instead we need to stop and ask ourselves, what do we see as our future in space in 5, 10, 50, 100 years? What do we want that vision and what do we want that future to look like? And what steps can we take today so that we can work towards that future tomorrow? So we need to keep our eyes on where we're trying to go, and we need to push towards it, not just with determination, but with genuine excitement and enthusiasm for what that future in space could look like for humanity. Thank you very much.